Record. So guys, so let's remember where we left off. So polynomials we mentioned are just operations that involve addition and multiplication, and those operations allow us to group based on the number of times we had to use the input. So for example, if this is a function, it uses only addition and multiplication. Obviously it's polynomial, and I can rearrange it into polynomial form of the form -2 plus 4x plus x squared plus x cubed. That means here I use no x, here I use x once, twice, 3 times. You understand, right? So because of that, we have this polynomial form. Here is the general polynomial form. Good. And so we mentioned something about derivatives, right? We're going to learn how to take derivatives of polynomials, of any polynomial. We kind of started doing it last time, but let's review. So first, obviously, the derivative of a constant is 0. Would anybody remind me why the derivative of a constant is 0? Because geometrically, constant y equals c, let's say y equals 7, y equals pi, y equals to -3, is what? All of those things are horizontal lines. Thank you. Slope is 0. And we are just, thank you, Alexander, right? So we report the slope of that line that we begin to see. Make sense? As simple as that. Nothing more, nothing less. Now, it's also very easy without any calculations to figure out the derivative at any point x of the function y equals x, right? And that is what? I just, for any x, the result is 1. Everybody sees that, correct? Do you see why it's 1, guys? Because zoom in on the line y equals x, what are you going to see? You're going to see the same line. And therefore, you're always noticing the same slope, and that's what you report when you do the derivative. Good? Now, we go on and examine the derivative of x squared. Now, without doing any calculations, it's a bit difficult to say what slope we will see when we zoom in. But we can carry out this process. We take the limit, z squared minus x squared over z minus x. We factor it out, we cancel the z minus x, and the limit becomes 2x. Are you with me? Now, what does the derivative equal to 2x mean, guys? It means, notice, don't pay attention to the x. It means that if we have a parabola there, then the slope is always twice. If it's basically, if the second coordinate is the square of the first coordinate, the slope at any point is twice the first coordinate. You understand? Guys, and when I mention that, you understand, when I say slope is twice the first coordinate, in my mind, there is no x. It's just crutches to help me communicate meaning. But if I just focus on the x, I'm not going to see much. And today you will notice, hopefully, why it's important to realize what you look at. It's not just, you see, when you do mathematics, it's not just the answer is 5 or 2. That's usually not even the most important thing. The more important aspect is the quality. What is it that you're talking about? So now let's try to take the derivative of x cubed. For that, we need to factor z cubed minus x cubed, the difference of cubes. Do you remember that, guys? We did it last Tuesday, I believe. So we need to do that. If you don't remember, you naturally go and practice the long division. You have to know long division. That's prerequisite for this class. If you don't know it, you're welcome to stay after class. I can give you examples. We can practice it. But you must know long division. Good. So I do long division here, and I see that the factor is z squared plus xz plus x squared. Do you see that? So I can write z cubed minus x cubed as z minus x times z squared plus xz plus x squared. Notice the pattern. Z is raised to a power 1 less than 3, and then z gives its powers one drop at a time. One drop, then another drop, then another drop, until there is no z. It gives all its powers to x. Do you see that? It gives all the powers to x. So I get z squared plus xz plus x squared. That's what remains. Look at what happens here. Do you see that when I take the limit? each z becomes an x now, and I see that it's an addition of x squared 3 times. So I get 3x to the second power. Now guess what's going to be the derivative of x to the power of 4. Can you guess a formula? I think you already did it last time, but just let's see if your mind is fresh. What is going to be the derivative, you think? Exactly. We have 2 guesses, 3 guesses. Yes. It's going to be 4x cubed. Very good. 4x cubed. Now, how do we verify that's the case? So again, we can use long division, and we notice a similar pattern. Do you see what we notice? It's z to the 4 minus x to the 4 seems to be z to a power less than 4, so it's z cubed, plus z squared x plus x squared z plus x cubed. Do you see what I pay attention to the z? 2, 3, 2, 1, 0. Z will give, it has now 3 powers. It gives each power drop by drop to x until there is no more z. You with me? You see the pattern, guys, right? So what I try to teach you is A, to retrieve the pattern. You can use long division to see what it is and then to remember it. And here is now what it allows us to factor z to the 4 minus x to the 4. I can factor out z minus x. I can simplify with the denominator. And when I push the limit, I get x cubed, x cubed, x cubed, x cubed. I get 4 copies of x cubed. Therefore, it's 4x cubed. What does it mean, guys? That means that if I have to differentiate a curve, if I'm zooming in on a curve where the first coordinate is, where the horizontal coordinate, to be precise, first, second, where the horizontal coordinate is some number and the vertical coordinate is that number to the 4th power, then the derivative is just the horizontal coordinate to the power 3 multiplied by 4. You understand? Take the horizontal coordinate, multiply it by itself 3 times and multiply that by 4 and you get the slope. You understand what I'm saying, guys? So the fact that there is an x doesn't matter. The derivative of x to the 4 is 4x cubed. The derivative of 4y, so of y to the 4th with respect to y will be 4y cubed. It doesn't matter what letter you use as long as you understand the meaning that the letter is supposed to convey. Now, we want to understand in general. We don't want to do it just for the power 3, 4, 5. You know, we get tired with long division. We want to do that once for all integer powers, for all positive integer powers. Yes? And how do we carry that calculation? Here we go. We are going to claim that z to the n minus x to the n is z minus x, and in parentheses z to the n minus 1, then x, z to the n minus 2, then x squared, n minus 3, and onwards, right? Now, how many terms am I adding here? You see what happens, guys? It's z giving its powers 1 by 1 to x. So you first will see, if it's z to the n, you will first see z to the n minus 1, then x, z to the n minus 2, and so on, until there is no more z. How many terms are we adding? Look at it. We can actually count the number of terms by the power of x. You see, this is 1 term. This is x2, so this is second term. All the way to here, we have n minus first term. So we have n minus 1 terms plus the extra one that does not have an x. And this is extra 1. So together we have 1 plus n minus 1, which is n. So the summation breaks into n terms. Are you with me? Now, whenever I think of it, I remember Oscar Wilde's The Nightingale and the Rose. Now, if you understand my analogy, maybe you can predict it here. In this example, what is the nightingale and what is the rose? In factoring nth powers. Did you watch that clip, guys? I mean, I'm asking you Nightingale and the Rose. I sent you a video. did you see it? You did not? Oscar Wilde? You haven't watched Oscar Wilde? You not even listened to it? Shame on you. How many of you watched that video? My question is, the first question, did you watch the video I asked you to watch for the class? Okay. Well, the rose is not N, right? The nightingale is indeed Z. Watch that video. It's just 7 minutes long. It's Oscar Wilde. He's a great author. He's an English writer, in particular Irish writer. Good, very, very famous, very good writer. Well, it's fine. You can read the book. There are many books, right? Oscar Wilde is famous for The Picture of Dorian Gray and many other stories. The Importance of Being Earnest, that's a play. And other things, right? So he wrote also children's stories, or I'm not sure if it's a children's story, but The Nightingale and the Rose. So there was this young man who was in love with a girl, and she would not dance with him unless he brought her a red rose. And there were only white roses in the garden. And so the young man was so sad that the girl will not dance with him, and the nightingale, who understood love, he heard the pleas of that young man, and what he did, he went to the white rose, impaled his chest on the thorn of the rose, and sang to the rose until his blood dripped one drop after another and made the white rose red. And he died, and the rose became red and beautiful. Yes, guys, and you can see that summarized in one line. Z to the n-1, Z to the n-2, Z is giving its powers drop by drop to X until there is no more Z, until there is no more nightingale, and there is only the rose in full blossom. The X to the n-1 is that rose. But really, if you understood that story, who is the nightingale? It is me. I am the nightingale, but you are not the rose. You understand? Because the way the story was over is that the girl did not care about that rose at all, and the young man, seeing that she is not of a particularly nice nature, said, "I'd rather study philosophy." Good pursuit, and he threw that rose into the gutter. It was for nothing. Just like most of my efforts, as I sit here hours upon hours, right, encouraging you to study or read or be interested, right? It is definitely the reason I remember Z to the n minus X to the n, as it is a very short summary of that beautiful story. So sad for me, exactly, right? But it's of course the nightingale's fault, you might say. Right? You are the young man or the young woman, it doesn't matter. Now, let's listen to how we can verify that the pattern is true. Do you understand, guys? Long division might make you notice the pattern. Your ability to see that there is a pattern might help, but how do you prove that pattern is always working right? Here is how you do that. So guys, I'm going to show that S equal to Z to the n-1 plus X Z to the n-2 plus X squared times Z to the n-3, so on. All the way to X to the power of n-2 Z plus X to the n-1. I wrote a lot of terms in hope that that somehow will catch your attention. So I'm going to show that z minus x multiplied by s will be indeed z to the n minus x to the n, thereby confirming that I noticed the right pattern. Yes? Now let's begin doing it. Let's, what we can do, guys, is I look at this, I can multiply s by z. So z times s, and write the terms carefully, is what? It's x, sorry, it's z to the, I'm sorry, it's z to the power of n plus x z to the n minus 1 plus x squared z to the n minus 2 all the way to x n minus 2 z squared plus x n minus 1 z. You understand? I just multiplied this top line, this s by z. And then I do the same thing, the top line I multiply by x. So x times s, it's what? It's x z to the n minus 1 plus, erase it, plus x squared z n minus 2 plus x cubed z n minus 3. Here we have x n minus 1 z plus x n. And I subtract. If I subtract here, I have z minus x s. I hope you see that. It's zs minus xs, I can factor out an s, yes? Z minus xs is equal, and now look what happens here, guys. Now look carefully. Look at this term, x z to the n minus 1. This will be canceled with, so the second term of the top line canceled with first term of the bottom line. Similarly here, look at it. Third is canceled with second. Right, and so on. This would be canceled with something in here, right? This will be canceled with something in here. This is canceled with something in here. What survives? You understand what happens, guys, right? It's just it's on a diagonal. Second term on so each term here on above is canceled by the prior term of the addition on the line below. I hope you understand what I'm saying. So what survives is this and this. So we get, just as we wished, z to the n minus x to the n. Good? That's just a verification. Again, guys, I hope you understood what it was at least for. I'm not sure if you followed or care to follow what it is at least for. I mean, you have to be able to naturally arrive at the pattern and prove that the pattern is true. That's very important in mathematics. It's very important for thinking. You notice a pattern, how do you do that? And then how do you establish that the pattern is always true? Good? Long division will give you the pattern. But you are not going to do long division for z to the million minus x to the million, right? So you will notice what's the situation, how it works, and then you explain it. That gives us, guys, that gives us right away a very impressive formula. We right away can prove that the derivative of x to the power of n is n x to the n minus 1. We prove that the pattern that we observed is always holding. That's called the power rule for differentiation. We have our first shortcut. So here, guys, we carry that calculation. We go by the definition, z going to x, f of z minus f of x over z minus x. Now I factor out z minus x. Here is that formula. This is what's left, guys. Do you agree? I mean, factoring already worked it out. This is that factor. Yes? And then we push z towards x. Do you see what happens? So each term becomes x to the n minus 1 because the sum of the powers, you understand, the powers that the rows gave, the droplets of blood that the rose has plus the droplets of blood that the flower has together make n minus 1. Do you see that? which means that in the limit, what happens? In the limit, each term that I'm adding becomes x to the n minus 1. How many terms we have? I just mentioned above. We have n minus 1 terms with some x and 1 term without any x. So altogether we have n additions. So we have n to the x to the power of n minus 1. A good student will not just listen to it passively, but when you go home, before you go to sleep, that might help you, some of you, right? What you do is you calculate the derivative. See if you can extract this formula by yourself. And you do that again and again and again until it is second nature, until it takes you not a few seconds even. What do we see? We see derivative of x to the 6 is 6x to the 5. Derivative of x to the 101, it's 101x to the 100. Derivative of x to the 30 is 30x to the 29. Understood? That's what we established. First shortcut, power rule. In the event the power is a positive integer, we see that it works. Next, guys, we establish, I think I mentioned those rules, but let me just go through them again. We established the derivative laws for addition and scalar multiplication. Good? So you have to understand what this means. What am I saying? I'm saying, suppose I have a function f that I know how to differentiate. The derivative of 5 times this function is just the derivative of the function multiplied by 5. Do you understand what I mean? So this first procedure allows me to carry derivatives of this form. So for example, if I have 5 times x squared, I now know that the derivative is simply 5 derivative of x squared, which is 5 times 2x, which is 10x. I can do those procedures if I establish law number 1. Yes? And I can establish law number 2. That means I'm adding 2 functions whose derivatives are known to me individually. So I know the derivative of f, I know the derivative of g. I want to express the derivative of the sum in terms of the sum of the derivatives. Yes? Now, how am I going to do that, guys? So I'm going to always go back to the definition. When I don't know something, I go back to definition. If I want to prove that something is true, I can go back to the definition. So it tells me, take this function evaluated at z minus this function at x, divide by z minus x, and then take the limit. And look at it. Within the definition of the derivative of the new function, I find the definition of f, the derivative of the old function. You understand? I need to know what am I searching within that pile. So I factor that c. Do you see f of z minus f of x over z minus x is synonymous with the derivative at x. So that's how I established it. Clear? Now, quick comprehension check. Quick comprehension check. By the way, hello, Grant. Nice that you made it. Quick comprehension check. When I'm trying to find the derivative of fx plus gx, and I do that by definition, let's say I call this function kx, okay? Then by definition, that would be simply limit as z goes to x of kz minus kx divided by z minus x. You agree? Now, within the definition, here is my question. What am I going to try to find? What expression am I trying to identify within it? Do you understand what I'm asking? If you're saying I'm searching for something, and I ask you, what are you searching for? You have to say, well, the keys, so I can help you find it. Or at least you know that you're searching for keys. But if you're searching for something and you do not know what you're searching for, it will be very difficult to find it. So what are you searching for? No. No, Sophia. Why Z? What am I searching for? Do you understand, guys, what am I trying to do? When I say derivative of f plus g, do you understand, guys? It's very simple. I'm just saying I have two functions. Individually, I know how to differentiate them. Now there is a sum of those functions. How do I find the derivative of the sum? Right? And so that means that I am trying to express the new derivative of the sum function in terms of the derivatives of the old functions f and g. So what am I searching for? Well, derivative of x is a bit weird there, derivative of f and g precisely. I'm searching for f prime x expression and f and g prime of expression. You understand, guys? Well, I mean x. I'm searching. I mean, right? Clear? That's a huge difference, guys. You understand? One reason it's easy for me is because, well, at least in some cases, I know what I'm looking for. So what is that, guys? So look what happens if I expand it. This is simply limit as z goes to x, fz plus gz. That's the function evaluated. That's k evaluated at z minus fx plus gx. Everything divided by z minus x. Yes? And look what happens, guys, when I regroup terms. Do you understand? I mean, I can group f together and g together, because why? Why do I want to do that? I presume I know those derivatives. So that's f of z minus fx over z minus x plus gz minus gx over z minus x. Do you see why I did it, guys? Do you understand that when I see fz minus fx over z minus x, I recognize the derivative of f. And in the second line, I recognize the derivative of g. I knew to do that because, I mean, I'm searching for those expressions. For each of them individually, I'm searching because I presume I know how to take the derivative of those functions. And I get that the derivative is f prime x plus g prime x. I see that the derivative of the sum is the sum of the derivatives. The formula is as simple as I like it to be. Good? All right. So here is what those formulas, and of course, for the derivative of the difference, you can either do it directly. Look at it, this. F of x minus g of x, you can either do it directly, or you can recognize that it's the same as f of x plus minus 1 times g of x. So it's using laws 1 and law 2. So I don't need to separately establish that. But if I want to, I can. Good? When you practice, and you will see in a moment, we're going to go into very uncharted, complicated territory. When you practice, you don't want to just know the solution to this particular question. It's not 2 or 5. It's not the way you do it, guys. You have this choice. Either you memorize 400 or 500 pages and not be able to know anything if I give you a 501st page, or you understand one page. But understanding is difficult. Choose. Understand one page and you can add more to it. Doesn't matter. More exercise, you will solve all of them. Or memorize and fail. Here is what we have. Derivative of 5x cubed. It's that 5 derivative of x cubed, which is this, right? And then you know how to take the derivative of any polynomial because it's a bunch of additions, subtractions, and a bunch of x to different powers. And we know how to deal with each of them. We know how to take derivative of x to any integer power, right? So doing it slowly, it's the derivative of first function, 5 minus 5 times derivative of x plus a derivative of x cubed. Well, you get it, right? You understand, applying those three shortcuts allows us to quickly deal with polynomials. They're very easy to differentiate. You all see that, yes, guys? So I don't always have to go back to the definition. Here is a quick example, guys. Calculate the derivative of 10 minus x squared plus 7x cubed. By the way, some people get so terrified that when they see it on the exam, they always go by definition. Notice I say calculate. I didn't tell you how to do that. So you can use anything you like. All right, Aaron. All right, Alexandra. Okay. Yeah, so by the way, somebody noted I made a mistake here. It should be minus 2x plus 21, right? 7 times 3 is 21. I accidentally wrote 27, but no problem. Yes? Yes, guys? You understand how that is calculated, and you could do it slowly if you had to. Right, so I might, of course, give you a question like this, and I say, find the derivative by definition. And if you, of course, know the shortcut, it doesn't matter, right? If I say find by definition and you don't do that, you didn't answer my question. Good? But so always read instructions. If you worry about the exam, look what is asked and do as asked. Okay, guys, now help me. Let's see if you could calculate the derivative of 2 to the power of x. You can say, you know, or you can say, oh, that's obvious. Go ahead, carry the calculation. Tell me what's derivative of 2 to the x. What would you write if you were asked to do that? You understand what I'm saying, guys, right? So we have 2 to the x. We're taking the derivative of 2 to the x. If it were on your exam, what would you write? So you're saying it's the same as 2x. Elazar, be careful. It's x, so it's 2 to the power of x, right? So I myself had this problem. It took me a while to adjust left, right, right, left, right? To me, 16 and 61 at some point look the same. But the reason is because in Hebrew, they write one way or another, right? So it was confusing me. That's partial reason, but you adjust. Okay, so interesting. Some things that people write are, right? Of course, guys, I mean, maybe I prime you or no. I mean, why isn't it simple? Why don't I see a lot of answers right away? Something bothers you? Didn't we just do some product rules? I'm so sorry, some power rule. Or you all watched Indiana Jones? You know you don't want to misstep. All right, I guess you don't want to be fun. You're not fun. In the morning, my God, they all just spat at me like it was spitting one after another. The answer, right? The answer is, of course, guys, look at it. Remember, a derivative of 2 to the x. We have the power x, so we drop the power x and we take 2 to the x and write minus 1. Wasn't it hard? Right? We just take the power, drop it down, and subtract 1. Do you understand it? No, you don't, right? You do not, or do you? Somebody said yes. Some say no, I do not. That's not correct. Some people, okay, well, I mean, some of you decide to not be fun. You see, maybe you've seen some sort of performance. Of course, that's not right. But it surprises me that nobody decided to say, maybe you lost consciousness by now. It's in the evening, right? I don't see all of you. All right. Or you know how to behave under interrogation. Right? You keep your tongue behind your teeth, right? Keep your mouth shut. That's what you're doing? So guys, you see, this is what people write. To me, when they write it, I imagine that what you're mistaken is this. Look at it. When you say that when you drop the x, you are confusing x squared and 2 to the power of x. Right? Now, what is x squared? In the bottom, the s is changing. It's moving around, x squared. But the head is staying the same. So it's x squared, right? But 2 to the x, it's entirely different, right? The base is fixed, but the power is changing. The head is moving, right? So when you are confusing between those two, I imagine you're confusing between a face this way and a face this way, or more precisely this, an ass with a head or an ass with a face, which is a very strange confusion. Let's review quickly what is exponentiation. Maybe me. So look at exponentiation. Let's understand what is a cubed. A cubed, right? A cubed just means take a number and multiply by itself 3 times. We're going to quickly segue into a brief review of exponentiation before we think about the derivative, right? So very, very brief and very confusing because it's not accurate at all. Are you there, guys? So look at it. What is a to the power of n? When n is an integer, that's just a shorthand to say multiply the number by itself n times. And then you notice the following rule. Look at it, guys. If I have a cubed multiplied by a squared, that's what? That's the same as a multiplied by itself 3 times and the result multiplied by twice a. And altogether you have a to the power of 3 plus 2. You see that? And it's very easy to establish that rule. In general, a to the n times a to the m, it's a to the n plus m. Agreed? For any integer, because all that is saying is, look what it is saying. This is saying that if you multiply a by itself n times and multiply the result by m many a's, altogether you have a product of n plus m many a's. You with me? Guys, you understand what we're trying to establish or semi-establish the power to addition rule, right? So we have addition of the exponents corresponds to a product like this. You know that from school. With some effort, with quite a lot of effort, you can generalize this to any real number. You have to actually first understand what it even means to exponentiate to a real number. You understand? When it's an integer power, when it's x squared, that's easy. Right? Let's review quickly just a few exponentiation ideas, guys. So tell me, so you understand this is understandable, right? This just means a times a times a. Yes? Could you tell me, please, what does this mean? A to the power of minus 1. What is that? Why is it 1 over a? Now, why is that notation going to give me 1 over a? Do you know why? Because it's telling a story. You understand? You can imagine that there is a battle between the a's in the numerator and the a's in the denominator. Negative power is involved, but that's memorization. What are we trying to communicate? We're trying to communicate a story. Okay, now what's that story? Look at it, guys. So suppose I have a cubed divided by a squared. We have a times a versus a times a. Do you agree? And you understand when you divide by a's, that means you cancel some of the multiplications. So what happens here, guys, look at it. Some multiplications are canceled. You see that you're left with a to the power of 3 minus 2, which is a to the power of 1. Yes? If on the other hand you had more a's on the denominator, look what happens. If I have a squared divided by a cubed, what I want this means exactly what? It means a times a times a times a. It's 1 over a, and I want the same subtraction rule to work. I want this property to be true. A to the power of m divided by a to the power of n. I want it to be a to the m minus n. That's how I begin developing it, yes? If I want this to be true, that means that this should be a to the power of 2 minus 3, which is a to the power of minus 1. It's not arbitrary. Why do you reciprocate? It's not arbitrary. The notation is dictated because of what you wanted to communicate. It means there was a lone survivor in the denominator. Yes? There was a lone survivor in the denominator. Now, if you understand that, please tell me what is a to the power of 0. If you understand that, tell me what's a to the power of 0, please. Why is it 1? Why? Why? Yes, you all see it's 1. Good, you remember. Why is it 1? Give me a very easy explanation. No survivors, exactly, right? And for everything, by the way, you see, guys, you don't really, yes. It's not, you mean division, Alexander. You mean a cube divided by a cube, not subtract, yes. Yes, so it's this, guys. I can say it was maybe a to the 1 divided by a to the 1. There were no survivors. That's just 1, and that's so a to the 0 has to be 1. Of course, guys, just to be clear, what is 0 to the power of 0? Does it make any sense? 0 to the 0? Undefined. You understand why it's undefined? Because that means there was a battle of zeros. Some of them were perhaps in the denominator. That makes no sense. If you understand why, at least commonly, it doesn't make sense to divide by 0. Okay, that's again, guys, it's very artificial. If you think that you cannot divide by 0, it's only in the way in some algebraic ideas. I divide by 0 all the time. 1 over 0 is infinity. You use those things in complex analysis. See, because infinity in complex analysis is an actual point in space. You understand? So it's all a matter of what you're trying to express. So when you say division by 0 is undefined, I mean, you know, to a point. So that's, we're gonna say this, that means nothing. We don't assign a meaning to that symbol. Now, another thing, guys, could you tell me why a to the power of, so we're assuming a here is bigger than 0. Why a to the power of 1/2? Why is that the square root of a? Could you tell me that? Why do I use 1/2 as a symbol for square root? Any ideas? Dividing what, Razar? I'm saying a to the 1/2. It's the square root of a. Why am I using that symbol? All right. Let me tell you then why. Perhaps that's actually not bad. That's very good, Erin. Their addition, you know, a to the 1/2 times a to the 1/2. If I want the powers to add up, that will be 1, right? So what Erin said is a good idea. So look at it. What is the square root of a? It means find me a number that if I multiply the number by itself, I get a, right? So if I say something like maybe the number can be written as a to the t, then a to the t times a to the t, it would be a to the power of 2t, and that's supposed to give me a. But that means that 2t is equal to 1, which means t is equal to 1/2. You understand? Those symbols are not arbitrary. Clear? Because you're trying to create, basically you're trying to create the play of the powers. They behave like addition, multiplication, you know, all that stuff that they do is supposed to stimulate the process that a undergoes. Clear? So for example, you have this law, which we will have to learn later. If you have a to the power of m and you take it to the power n, that ends up to be a m times n. So you have to prove, you have to actually, when you start thinking about it, it's a very, very nasty matter. And then, guys, there is still something that you don't know at all, right? You think, okay, maybe you can understand what it means to take the power of 1/2. Suppose that you even understand the meaning of it. What would you think it would be to take a to the power of pi? So it's a to the power of 3.14 and onwards, right? So even such expressions are possible. Or it's possible to take a to the power of √2. And what does that even mean? So we have a lot of things that are not defined, and you never saw them defined. It's a problem, right? And so we have very little knowledge of exponentiations. But let's say that for the moment, we pretend that we understand what a to the x means, which is, by the way, a huge lie. Right? It's a huge lie. We don't understand what it means in some instances, perhaps. Let's pretend that we understand what a to the x is. And then we have the following rule that we can somehow hope to establish. It's that a to the power of x plus y, it's a to the x, a to the y. Okay? You can verify this to be true for integers easily. You can try and make it work for fractions, right? It's kind of, let's consider it good enough if you understand it for integers. If you want to work a little more, try to see if you can understand why it should work for fractions, for any rational numbers, right? And so, guys, now we're going to try to take the derivative of a to the x. Are you ready? Now, there are two definitions of the derivative, guys. Up to now, we prefer the definition z going to x. Let me briefly review what those definitions are saying, and why are they exactly the same. We have two notations. Look at it. So if I take the derivative, I have notation 1, which is f prime x. This is limit as z goes to x, fz minus fx, z minus x. Yes? Now, what is that saying, guys? Look at it. What is that limit saying? We're saying we have a graph, we have some curve, we have the fixed point x, and this is f of x. So this point has two coordinates, x, f of x. We are going to select another point, and it has coordinates z, f of z, and we are going to draw a tangent line through those points, where the point z will approach x, that will make this point on the graph approach the black point. Clear? That's what this is communicating. So we're saying z is going to be a number close to x. Now, here is the second way of communicating the same idea. There are many other ways, possibly. I'm not saying those are the only ways. The other popular way is to say f prime x is equal to limit where h goes to 0 of fx plus h minus f of x divided by h. Good? So what are we communicating in this situation? In this situation, we communicate, again, very similar idea. Here is my point x, f of x. And here, all I'm saying, guys, I'm just saying, oh, pick a point that is like x, but not exactly. X with a slight blemish, with a slight imperfection. That imperfection is called perturbation. In other words, it's something that makes it not x. You understand? And so I emphasize x hat or anything else, right? I emphasize it's not x, and I just try to say, oh, this point is like x, but not really. Right? So I'm thinking of language. I'm saying like x, so I write x plus h, which means not really. You understand? And so here we have that other point, and again we're having the same situation. Again, we are if h, the thing that makes it not like x, is going to be small, this point will go here, and this red point will be merging to the black point. They are saying exactly the same thing, guys. Right? If you see the sentence that looks differently, one sentence looks not like the other, but they are saying exactly the same thing. You see, it's the analogy I would say is I can say my name is Arkady. That's one way to say that. I can say something like Arkady is the name by which I was called. Or something like that, you understand? So you can make all sorts of many sentences. Elazar, so you want to be Arkady, it's your name now, huh? You want to be Boris Godunov, a wrong Tsar. So you understand, guys, that they just mean the same thing. But have you ever been in court, right? You can state the same thing in different words. And if you choose the right words, you can get a very different outcome. You know that, right? So when you stand before a king or before a judge, you choose your words carefully. Do you understand what I mean, guys? So mathematically, the meaning is the same. Psychologically, no. Psychologically, one idea might inspire one direction, and another wording will inspire another direction of thought. Even though more or less you cannot distinguish between the sentences in their logical content. Do you understand what I'm saying? And we're going to see that this is the first time, guys. You understand? We never prefer this second version. This is the first time we prefer the second formulation of the derivative. Before, for all algebraic functions, we preferred the first, the f of z minus f of x version. Yes? You agree, guys? Now we are going to prefer this one, and I'll show you why. Look what we can do, guys. Now, this is entirely different. It's nothing like you were doing before. We're going to see if you recognize what you are looking at. And pay attention very carefully, okay? So look at it, guys. So I begin trying to take the limit. This time I use this definition. First time I prefer it. So I take limit as h goes to 0. I have a to the power of x plus h minus a to the x divided by h. I am going to look at it. It's a sum of two powers. I'm going to write it as a to the x times a to the h minus a to the x. You understand what I did, guys? I wrote the sum of powers. I translated it into a product. You see that? Now from here, you all see I can factor out a to the x. Guys, are you with me up to this line? Are you with me up to this line? You are, all of you. Confirm with me, guys, that I want to see as many of you as possible. That if not, I will try to re-explain if I have to. Now, I'm going to ask you a very difficult question, or maybe a very easy one. Okay? Now, listen to me carefully, guys. You see, I mean, I just did algebra. Here, it's all algebra. I factored x to the x, h, and I have this limit. I'm going to ask this. What is that limit? And I'm not asking you to solve. Don't give me a number. I'm asking you, what is it? And in that sense, guys, imagine I walk very, very late at night and I hear moo. Where am I located? Right? You can right away imagine where I am located. A farm. My God, you see, guys, I didn't have to explain too much. You said right away a farm. And the creature that is moving, you right away can imagine it has 4 legs, right? It's grass. I am not asking if her name is Bessie. No. I'm just asking you, do you recognize a cow? That's what I'm asking you here. What is this limit? Do you recognize this cow? Qualitatively. You see, some people listen to me, but they say 0. I didn't say what it is. I didn't say what it is, guys. You say infinity, 0. I ask you to recognize what is the cow. Or not cow, maybe it's not a cow. You understand what I'm saying? Give me the species. What am I doing there? What is that limit? You see, you don't have trouble when I said moo. It should be the same way. That means that you understand cows, but do you understand this? No, I didn't ask you. No, maybe not. No, 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 no. No. Look at it carefully. What form does it have, guys? Look at it. Look at the first limit. Let me give you a hint. You see the first limit? I ask you, what is this thing? You would say the derivative of the exponential at the point x. Yes, this is the derivative of the exponential at the point x. What is the limit that I end up? Look at it. You see this thing, guys? This thing is this the definition of the derivative at x. Before I even do any calculations, I need to recognize what is somebody doing. So in other words, you see, I wrote here f prime. But if you erased it and asked me what is this, I would say, oh, this person is trying to find the derivative of a to the x at the arbitrary point x. That would be my reaction immediately. Understand? Somebody is trying to find the derivative of an exponential at an arbitrary point. That's what this is to me. If this is so, then what is this? Don't solve it. What is it? Well, you're labeling it as limit, but what is it? No? The derivative at where? You see, Abhishek, you might know some from it before. I'm asking you not, yes, at 0. This is the definition of the derivative at 0. Look at it. What I'm seeing here, it's just the limit at 0. Let me try to explain to you what just happened here. You understand? I did not solve it. Are you with me, guys? I did not solve the limit. I didn't find what it equals to. I didn't say it's 0 or infinity or anything. I sidestep of it. What I did is first I said, what am I even doing? I am finding the derivative at 0 for that function. I began searching for the derivative at an arbitrary point, and I end up needing to find the derivative at the point 0. Are you with me? Do you understand what I'm saying? The sentence pushes me into that direction. If I look at the sentence, I'm saying, oh, I am now trying to find the derivative at 0 of the exponential function. That's a very important type of reasoning. Let me show you what I mean graphically in case you don't see it. Here is the graph of 2 to the x. Good? What am I going to do if I want to find the derivative at this point, guys? You see? This is a point. I want to find the derivative. What am I going to do to search for it? I do what? I zoom in, right? And I hope to see a straight line. Agreed? So here, let's zoom in. Let's make it at the point 4. You don't mind, right? Let's zoom in at the point 4. You see now it looks like a straight line. Do you agree? I zoomed in at the point 4. It begins to look like a straight line. I'm trying to measure the slope at the point 4. Now my procedure over there tells me what? Tells me that to find the derivative, I just have to take 2 to the power of 4, multiply it by the slope that I obtain when I zoom in at 0. Do you understand? Look at the formula again, guys. Look at it. I'm told that if I try to find the slope at an arbitrary x, I just need to multiply a to the power of that x by the slope at 0. Do you understand what I'm saying, guys? I didn't solve it. I don't know what the slope at 0 is. I just realized that the limit is telling me, oh, to obtain the derivative at the point 4, take 2 to the power of 4 and multiply by the slope of 2 to the x at 0. I always look at 0. Let's zoom in, zoom out. Let's look at 0. Here is what I have to look. I have to look at that slope. And if I know that slope, I will know it everywhere else. In particular, the function is differentiable as long as it's differentiable at 0. And if it's not differentiable at 0, it will not be differentiable. Are you with me so far? You look like you're staring into headlights. Are you with me? Like, right? You understand what I'm saying, guys, yes? It's not too difficult, right? I mean, I didn't say something unimaginable. I said here, the sentence is just pushing me into that direction. I see that I try to find the slope at some arbitrary point x, and I realize I need to find the slope at 0. Good? Confirm that you understand. I don't log Grant. If when I zoom in the point 4, what I do according to this exercise, I just take 2 to the power of 4 and multiply it by the slope at 0. Slope at 0. I take 2 to the 4. 2 to the 4 is 16. So I take 16 and multiply by the slope at 0. Do you see that? You see how you see that, guys? It's not me who is telling you that. It's mathematics. You make mathematics speak. You understand? So that one of the greatest mathematicians of the 20th century was Gödel. And Gödel was able to make mathematics speak to him, like it had conversations with him. You understand what I mean by that? He was able to make mathematics tell him what it cannot prove. It's called Gödel's incompleteness theorem. You see, so you can make, if you are very good at something, you can make it talk. So do you see what happens here, guys? Again, how are you making it talk here? We are saying we're trying to find the derivative at an arbitrary point, and we realize it's the function itself times its derivative at the point 0. Now, could that derivative at the point 0 be equal to 0? Could you tell me that, please? Can you, let's see if you have intuition. Can that limit be possibly 0? Why or why not? Can it be 0? I'm not saying exactly, but okay, so maybe I should say a little bit more. There's no division by 0 here. It's not what's happening. So let me just try to bypass, guys. So you see, it's a difficult limit. Some people said what it equals to, but we'll mention it later, right? I mean, if you are trying to find this limit by yourself, you need an entirely different strategy. It's not calculation that you want. Okay, it's some sort of strategy. Okay, let's assume for a moment this limit exists. If that limit exists, it's the derivative at 0. Look at it. If this is my function, then the derivative is the original function multiplied by the derivative of this function at 0. Do you understand? And that, even without knowing what that derivative at 0 is, tells me that the function is not very changed by taking derivatives. It almost stays the same. Do you understand what this is saying? So for instance, for some, I do not know what that number is, but suppose for example, if I take the derivative of 5 to the x, I know that the derivative will be some sort of thing like 5 to the x, and maybe multiplied by some number. Maybe that number is 3. Maybe. I do not know what that number is, but it will be by some number that 5 to the x is multiplied. It's not very significantly changed. That's all I understood about this function so far. Clear? All I know is that the derivative is not going to be very different, and exactly from the function. And what is it exactly? If the function is f of x equal to 5 to the x, the derivative at x will simply be the derivative at 0 multiplied by f of x, which is simply the derivative of 0 times 5 to the x. You understand? I was not able to solve it. Guys, is it surprising to you? Look at it, f prime of 0. You, when you solve the equation x squared minus 2 equal to 0, you give me solution like x equal to root of 2. But if I ask you without a calculator, what is root of 2? Can you tell me? It's exactly the same thing we do here. We pretend that we solved it. We give a labeling and say the solution is the derivative at 0. Here the solution is the root at 2, but you haven't calculated it, right? Not in the sense of, let's say, if you calculate x squared minus 25, you can say equal to 0. You can say, oh, x is equal to plus minus root 25, which means x is plus minus 5, right? You kind of here told me what is the root, but here you keep it as a riddle. You say the root, the number that if multiplied by itself gives you 2. So here we say the number that represents the slope of the tangent line at 0. Do you understand what I mean? You just gave it a name. You didn't answer what it is in some sense, but you gave it a name. Are you with me? I don't think I'm saying something like overly complicated, but yes? It's the same thing you were doing all the time, and you would have noticed if you thought about what it means, that what you're doing there. You are just giving something names. This is what happens. The derivative of a to the x is the derivative at 0 times a to the x. If you take another derivative, another f prime of 0 will pop out. Do you understand how that works, guys? They just pop out in front, right? So it's if the derivative of 5 to the x were 3 times 5 to the x, then the derivative of that will be the derivative of that, which will be 3. I put it in a circle because maybe it's not 3. Derivative of 5 to the x, which would produce 3 times 3 times 5 to the x. It will produce the extra 3. Are you with me? And so in general, so you see, when I take more derivatives, I'm just multiplying by that slope, if I could find it, of 0. Good. Let's try to say a little bit more about that slope. What might it be? So I want to try to estimate what I'm not going to calculate it exactly since it's a bit difficult, right? I'm now going to try to estimate it by the help of a calculator, with the help of a calculator. Look at it, guys. 2 to the h minus 1 over h represents the derivative of 2 to the x at 0. That represents the slope. So if I cannot calculate it exactly at 0, I will presume that if h cannot be exactly 0, I will make h close to 0. And I decided to make h 1 over 1,000, just because it looks like a very small number. You understand? Very number close to 0. So h is 1 over 1,000. So then I calculate 2 to the power of 1 over 1,000 minus 1 divided by 1 over 1,000. If you plug it into your calculator, you see that, guys? Plug it into your calculator, and your calculator spits the number 0.69 about. That means that the derivative of 2 to the x is approximately 0.69 times 2 to the x, right? Approximately that number. Are you with me? Confirm, guys, in the chat if you understand or you're bewildered entirely and you're lost. And if you're lost, I would like to know where I abandoned you. Well, can we solve the slope? I mean, to be precise, can we find the slope of the tangent line? There is no equation, right? Can we find the tangent line slope at 0? I didn't say that. I'm just, you understand, guys, right? So there are several ways to get into a building, right? Let's say, how are you going to go across fortifications? Imagine you're trying to attack a castle. You can try to break it with your head, Or you can try to outmaneuver, move around it and not even bother attacking it, and starve the inhabitants. They come out, surrender, and you have the castle. That's what we're doing. We will solve the derivative precisely, but not now. You understand? We are moving around it and continuing our attack, just seeing the form rather than being precise about it. There is nothing wrong about it. You did it all the time. You cannot tell me what is, without a calculator, what is root of 5 or what is root of 2, right? If I told you calculate root of 2 right now and you just had a pen and a paper, can you do that? So that means, and if you pressed in the calculator, that means, well, hopefully somebody who programmed the calculator knew what they were doing, but it was not you. So it's a similar thing here. For the moment, Jeffrey, we will get precise answers later on. Don't be worried, but we cannot hope to be always precise right from the beginning. We will get precise answers. You understand, guys? You have to also switch out of the mode that in mathematics, you are answering, oh, the answer is 5 or 7 or 12. No. In mathematics, you are communicating a concept. Just like you do when you write a book. Good? Exactly the same thing as you do with language. You communicate concepts. And what's the concept? We see that the function, the derivative of 2 to the x is essentially 2 to the x, but not quite. Okay, where did the 1 over 1,000 come from? Would anybody answer that question? Why did I pick 1 over 1,000 or 0.001? Would anybody answer that question? It's close to 0. It's the hat, precisely. You understand, guys? It was completely arbitrary. I could have selected a smaller number. I selected it with the hope that it is small enough. In fact, I could have selected a larger number, perhaps. Look at the graph, guys. Look at it. I am asking myself, when near 0 does it look like a straight line? This is completely experimentally. See, I'm zooming out. Zooming out, zooming out, zooming out. You see, this is the function near 0. This is 2 to the 0, right? It's 1. It's the function near 0. Do you see that in the zoom? Look at it. I'm going to now zoom in so that my edges are going to be 0.5, about 0.5. You see? So do you see? I now zoomed in. It still kind of looks crooked. Let me zoom in more. You see, this is now h equal to 0.1. Here it is, right? Let me zoom in. Zoom in. It kind of looks like a straight line. So you might have even selected h equal to 0.1, perhaps, based on that picture. You understand? It's just an approximation. What I did is I actually was very cautious. I selected an h. Look at it, somewhere here. You see? So it's very close to 0. I wanted to select the closer, the better. The closer, the more like the derivative it will look. You follow what I did, guys? But it was completely arbitrary. It was just out of hope. I was hoping that that would be close enough. So do you understand how I got the 0.69? I didn't even get it. I allowed the calculator to estimate this number. Good? You are with me, guys? No trouble, right? You see, it's very simple. Look at it. Just apply the definition of the derivative and realize that there is now a part that you're not able to solve. And instead of banging your head against it, just say, oh, the solution will be the derivative at 0. Just because it's a very significant. You recognize that you started the derivative at some arbitrary x, but you actually need to know the derivative only at 0. You understand? You don't need to bother with the slope anywhere else, only at 0. And then multiply it by 2 to the power of x. So if I want the slope where x is equal to 2 for the function 2 to the x, I just will take 2 squared and multiply it by the derivative at 0. You understand? If my point is 3, that's where I want the derivative, if x equal to 3, I just take 2 to the power 3 and multiply by the slope that I obtain at 0. I only need the slope at 0. Good? Here is that slope approximately. That's my best guess. So it's 0.69, 2 to the power of x. You all have calculators. I'd like you to carry out the same calculation from beginning for 3 to the x. You understand? Tell me what approximately is the derivative of 3 to the power of x. Approximately, okay? Okay, some of you are getting that somewhere. Good. More? Very good. A few more moments, I want more answers. Okay, Moshe, good. Let's do it now. So again, guys, right, I realize from the very definition, I realize that the derivative of a to the x is always a to the x times the derivative of a to the x at 0. I hope you understand how to do that. I mean, I don't care what you're using, Moshe, right? It's just to figure out what it. I mean, hopefully, you understood the definition, how you would arrive at that idea. Good. Do you see what happens, guys? The derivative at 0 is approximately 3 to the 1 over 1,000 minus 1 over 1 over 1,000, and that's slightly more than 1. Yes? So we have the number slightly more than 1 times 3 to the x. You understand what it means? Again, the function is not terribly changed. Look at this number. This number is slightly bigger than 1, and this number is slightly less than 1. Do you agree? If I were to take more derivatives of 3 to the x, then the derivative of that will be two derivatives. Again, take the derivative one more time. That would be 1.099 times the derivative of 3 to the x, which will produce an extra copy of 1.009. So that would be 1.099 squared 3 to the x and so on. You see? My point, you can continue taking derivatives, and the result is just every time you take the derivative, just multiply by that scalar. That's approximate. That's not the right solution, right? It's just an approximation. Kind of like when you press root of 2 in your calculator, that gives you an approximation.
Wait, so if you do a derivative of a derivative, you're going to square it? So in this case, if you do
Yes.
derivative, okay, fine.
Do you see why? Because the derivative of a scalar times the function is the scalar times the derivative of the function. And whenever when I take the derivative of 3 to the x, I have an extra 1.099 popping out.
Okay.
And that's approximately, that's not the true derivative. Because we didn't take the limit, we just said, instead of taking the limit, plug in a number that looks to be close to 0.
0 hat, yeah.
Zero hat, exactly, right? So when we cannot calculate, we kind of, well, we hope that the calculator estimates it well enough when we cannot calculate precisely. Good. Now, we can do it with 2.8. And we see that the derivative of 2.8 at 0 is approximately 1.03, which is even better, slightly closer to 1. Yes? Okay, guys, so just a few remarks that, again, I mean, I would be, of course, several things, right? So there were a lot of things here that we assumed. First of all, we assumed that by plugging in this number, we get a very good estimate. We had no reason, right? We just kind of did it arbitrarily. So somebody asked me, I think Jamal asked me why 0.001, completely arbitrary. I decided this looks to me close to 0, right? What, let's say 0.1 might be dangerous, and I was worried and I picked a small number. But what does it mean to calculate this quantity, guys? This quantity means that I need to take 1,000th root of 2. And you are not even able to do the second root of 2, right? So that's very, very complicated operation. How is the calculator doing it? Ask yourself, right? Somebody programmed it. Somebody had to figure out how to simulate that process. So first of all, we are relying on a machine, and we're hoping the machine is doing it right. And by the way, I can show you examples where the machine will be wrong, always wrong. Okay, even as quick and as sophisticated as it is, it's possible to make the machine be wrong because its operation will not work. So here is my my observation, guys. Okay, so notice that we take the derivative of 2 to the x, we multiply by a number less than 1. For 3 to the x, it seems that we're multiplying by a number more than 1. Agreed? Now, first question, guys. Could the derivative at 0 for any a to the power of x be actual 0? For any a bigger than, you understand what my question is? Let me write it. Suppose that you begin with some a bigger than 0. So could the could limit as h goes to 0 of a to the h minus 1 divided by h equals 0? My first question. Could that happen? And if you answer, of course, I want to know why it could or why it could not. Do you understand my question, guys? My question is very simple. Could the derivative be 0? Why no? Well, the answer is obvious, guys. What's the derivative of a to the x? Look at it. What's the derivative of a to the x? Derivative of a to the x is the derivative of a to the x at x equals 0 times a to the x. You agree? So it's always some constant times a to the x. Do you agree? It's always a number times a to the x. Now, if that constant is 0, what happens? If the constant is 0, then the derivative of a to the x is 0 everywhere for every x. Could the derivative of a to the x be 0? If the derivative of something is 0, what is that something? Geometric picture of it would be what? A horizontal line. Isn't it obvious, guys? So this is not a horizontal line. I don't need the graph to show me that. I can, if you want to, obviously I can look at something like this, or at something like this. I can see the graph, and you can see that it's not a horizontal line. But I don't need a graph for that. I know, for example, that a to the power of 1 is different from a to the power of 2. Do you agree? I'm naturally assuming a is not equal to 1. We don't want to deal with 1 for a moment, right? Not 1. A is not 1. A is not 0, bigger than 0, and not 1. Good? Do you understand? Now, my next question is, what would have been the best value for that limit? If you could pick a value, you cannot pick 0. Do you agree? 0 is impossible, because picking 0, you're saying it's a horizontal line. Now, we cannot have a to the x a horizontal line if a is not equal to 1. Agreed? Like 1 squared 1 to the x, you might say it's always 1, maybe. So my next question is this, guys. So we have a bigger than 0, and of course a not equal to 1, I should have mentioned. And what would you like limit as h goes to 0 of a to the h minus 1 divided by h to equal? Question clear? So instead of actually finding what it equals to, I'm asking you what would you like it to equal to? Okay, you say, Sophia says 0, why 0.99? What's the best thing you would like? Guys, look at it. You would have to multiply by it, right? So when you take the derivative, you have to multiply, exactly. You agree? Look at it. If I look at it, when I take the derivative of 3 to the x, I need to multiply by 1,099 times 3 to the x. If I had to take the derivative of 3 to the x 3 times, I will have to multiply by 1.099 cubed times 3 to the x. That's a lot of hassle. Do you agree? The more derivatives you have to carry out, the more hassle you are suffering. Good? So what's the best number? 0 cannot be. What's the next best number? Or maybe the equally good number? 1. Are you with me? It's on, you see, understand, you have to know what it's, I call it wishful thinking. You have to know what you're seeking. What is it that you want? Can you imagine? you go in front of a god and you can get anything you want, but you have no idea what you want. Tough luck.
Professor, do you mind just explaining again why you want it to be 1?
Well, because you look at it, if for 3 to the x, do you see that you are multiplying by a number that's not 1? Multiplying by 1 is very easy.
Okay.
I didn't say a equal 1, Sophia. I said I'm not asking for what a. I said a cannot be. You mistook my my question. I said what would you like the derivative to be. I didn't ask you for the base. Right? I didn't say you're gonna pick the base. Base is something else, right? I'm saying what would you like the derivative to be? Look at the question again. Do you see what would you like this limit to be? I didn't ask you about a. Yes? You want it to be 1. Do you all understand why 1? Avram, do you see why 1? Because look at it, for derivative of 3 to the x, do you see you multiply by a number that's not 1, and you have to calculate the cube of that number. That's not easy. You have to multiply this number by itself. If you want to do it without a calculator, multiply 1.099 by itself 3 times. And if I told you take a millionth derivative, do you want to multiply this number a million times by itself?
Okay, so it's more work, so you want it to be 1.
It's not just more work. I mean, you see, guys, if you don't feel it, you know, it's like, why would you like to dig with a tractor or with your hands? You see, it's that type of thing. You see, if it's not 1, you will be digging with your hands or with your teeth.
Oh, okay.
You see?
That makes more sense. Yeah.
That makes sense, guys? Right? But if it's 1, you don't need to do anything. The derivative is the function itself. Nothing whatsoever. If the derivative, if this derivative at 0 is 1, then whenever you take the derivative of that function, it will be the function itself, no change. Clear?
Yeah, thank you.
Very good. And here is, guys, what we're going to do. We're going to make a hypothesis. Our hypothesis is this, that there exists a number, we call it E, that is between 2 and 3, and so that the limit is 1. So this is that A that I do not know what it equals to. I mean, it seems based on the calculator games that it's between 2 and 3. I'm going to make that hypothesis. Clear? What this thing is, we are going to... The cat, I don't think he gets it. I mean, he just understands that he's not going to get out of here. Right? He's panicking. He's begging to be let go, to be allowed to be free and not listen to this lecture. But it's a black hole. No, he is not hungry, he just ate. Yes. But you know what they say, right, guys? No free food. He's looking at freedom, he's looking through this little slit. Yes, right by me, and hoping that the door will open. No. No. All right, so let's stop today's lecture since we have only, 2 minutes left. Of course, if you want to, we can play a round of what, when, where, but if not, I will not torture you. Goodbye. We can, of course, practice more questions if you still want something. All right, I'm stopping the recording.